Okay, so before I proceed for the day, we'll just have a quick look up that what we did in last class. Okay, last session it was 10th and 11th session, right? So for the in the 10th session we discussed about classification model. Okay, so while discussing about the classification model, we used a data which was wine data. Okay, and we did scaling. I just told you why scaling is required in KNN. Without a scaling, model was not that accurate. That's why scaling is required. Then we worked on training the model, and at the end we were making the predictions as well. Everything was working better over here, right? And then we worked on the cross validation as well over here, just to understand in case if I split the data for multiple times, like over here we are splitting it for 10 times, right? So after 10 times split, how will it behave? That we did through the we analyzed through the cross validation. All right. So that is what done. Thereafter, fine. And then I started discussing the linear regression part. I just try to explain you actually how linear regression works, right? The learning process, error optimization process, and finding out the best fit line. Okay. And then multiple linear regression, in which we were trying to use multiple features to build up the model. Okay. So these are the things that we did. Right, classification regression, right? Thereafter it was regression part, right? Then in the last session we started discussing on the non-linearity, right? And we tried to find out like how this was the starting of the first one was the linear, right? So linear. Sorry, I just lost the connection. Start once again. All right. So it was what I was saying. It was like we were discussed after linear, we discussed non-linear, right? In the non-linear, we identified that how can we create a best fit non-linear line. Okay. So for non-linearity, what we have to do, we have to make the transformation on the data. Okay, like x transformed into x square and x cube, and thereafter we are using this information x square x cube, right? And then we the relation between the actual feature and the predicted value will be non-linear, right? So after that, I told you to implement the non-linearity on the these two features, TV and radio. So have you tried? Anyone tried this thing? And I'm not saying that I am expecting a correct result, but just try, because if you don't start trying, right or wrong, it will be difficult. It will be difficult for you to learn the things, right? But if you start trying it, okay, even incorrect, whatever, random thing, okay, then only things will be better for you. Okay, so it's very important, because by just attending the class, things may not help that much. You'll get the overview, but practical understanding is very important, right? So if I'm saying you something to try, so in a week, whenever you get half an hour time, 1 hour time, whatever, just attempt it. Okay, whatever. Like for example, it's not getting any idea. Suppose you just look at this particular problem statement, you are getting no idea. At least you know that first you have to read the data. So at least try to read the data. Okay, start step by step. Okay, try with read the data. So like suppose I'm a person who had not good understanding. So what will be my approach? So I know that how to read the data. So first step, I just take my first step. Okay, import pandas as PD. Okay, import numpy as np. Okay, import matplotlib dot pyplot as plt. Right. Now I'll do what? I will read the data. Right. So let's say here is the data I have somewhere on the GitHub. Okay. Or you can download the data as well, or you can use it from the previous link as well. Everything is fine. Okay. So let's say, where is my data? Let me just read the data. Hmm, here is it, right? So first step, I'll just try to read the data, right? Once I have a data, then I'll again read the problem statement. Like it is saying that I have to use two features. Fine. So at least I know how to read the two features. Okay. Isn't it? At least what I know how to read the two features. Right. So for that, let's say I'll just read the two features over here. Right. And then the target column. Right. So now this one at least I know. Right. Now next thing is like people said that I have to implement non-linear. So here I am facing, suppose I am not sure like how to use it as a non-linear. So what do? I can just go to the kind of things that has been covered earlier. So for the non-linearity, what is done? Your x and y was transformed into non-linear things, like a 3-degree non-linearity. Right. So see, if you have a single feature, right? So non-linearity works like this. See, if you have a single feature, right? So non-linearity, works like this. X we transform into x. We just transform this guy. X we transform into what? X square, x cube kind of thing for 3-degree. If I have two x1 and x2, okay, then how non-linearity works? Okay, if I have these two entity called x1 and x2, then how can we use it for nonlinear regression? So it would be x1, right? I can just transform it like this, x1, thereafter x2, sorry, x2, then x1 is square, x1 into x2, then x2 is square, right? This is the transformation. Why? Because 2-degree nonlinear equation looks like this. X1 plus W2 x2 plus W3 x1 square plus W4 x1 into x2 plus W5 x2 square. Okay, the 2-degree nonlinear equation looks like this. Okay, for two variables. Okay, for what? For two variables. For a single variable, it is like this: x1 plus W2 x1 square. Here we have a single variable. So for only x1, it is like this. But when we have two variables, then it will be like this. Okay, this is a 2-degree nonlinear equation. That means now my model requires these many features to get trained, right? So if my model required these many features to get trained, that means I have to convert this x into, okay, what? Do perform, or first let's split the data from sklearn dot model selection import train test split. Okay, x train, x test, y train, and y test. That would be equals to what? We will split it, right? So this thing at least we know. Okay, even you should try, when you can't go with the non-linear, you should try with the linear also. But anyway, so now I have to do the transformation. So for transformation, what I did, this is what we used, right? From sklearn dot pre-processing import polynomial features. So from sklearn dot pre-processing import polynomial features. Then we define POL is equals to what? your polynomial features. Okay, this is object we define, and here what we define degree. Okay, so let's say we have over here degree is 2. I want 2-degree transformation. So as I want 2-degree transformation, then what I have to do? I have to write over here POL dot fit. Okay, what I have to fit? I have to fit X train. Right. So when I fit the X train, it will know that X train is having 2 components. Right. And then when we transform it, that 2 component will be converted into 5 component. Right. So when we just transform it, POL dot transform what X train. So it will be converted into 5 component. 1, 2, sorry. See. Here 1, 2, 3, 4, 5, 6. Okay, why it is 6 component? Because first is 1. By default, first is 1. For all of them, first is what? 1. As first is 1, so what we do, we'll just use over here include bias is equals to false. Okay, I'll say that no, I don't want that bias value at the beginning. So it is been transformed into 5 components. Okay, why it is 5 component? Because we have x1 according to the equation that I told you. This is what? This is your x1. This is your x2. This is x1 square. This is x1 into x2, and this is what? X2 square. Fair enough? Same way, it's for the second sample, third sample, fourth sample, fifth sample, sixth sample, and so on. Right? So it means what? Your data can be easily transformed into polynomial feature. X train, this is polynomial. Okay. And the same way I can transform the test data. Right. So X test polynomial. Fair enough. So we can transform your train and test data quite easily. Right. And once it is transformed, next what? Everything is sorted. Just import the algorithm and train it from sklearn dot linear model. Import linear regression. Okay. So model A is equals to what? Linear regression. Right. Thereafter, what we do? Model A dot fit X train polynomial comma Y train. Okay. So when we train this guy, my model is trained. Now, can anyone let me know how many coefficients we will have? Once I train this model, so how many coefficients we will have? That means how many trained parameters? Please tell me.
Four,
Right now
four,
we have
sir.
a 5.
5, right? Because we had converted 2 features into 5 components using polynomial transformation. So obviously we will have 5 coefficients. Okay. So if I will print this thing, okay. So this is a 5 coefficient. Okay. So now using with prediction will be. Now we have to evaluate. So for the evaluation, we'll do what? Model A dot predict X train scaled or X train polynomial. So it will just make up predictions. So these are what? These are the predicted value Y train predicted. And same way we will make the prediction Y test P is equals to model A dot predict X test polynomial. Right. So it's like we made the prediction as well over here. Right. Now we can do what? We can just identify the accuracy over here by using Y train minus Y train predictions. Okay. And here it's like when we calculate, we get the average error. Sorry, we have to calculate, make it absolute error. Okay. And thereafter I can take the mean value. Okay. So what is this? This is your mean absolute error on the train data. All right. And thereafter we can have the mean absolute error on the test data as well. So can anyone let me know what was the mean absolute error on the train and test data for predicting the sales last time? on train? Can anyone tell me what was the mean absolute error on the train and test data when we use two features? Last time when we used two feature, what was the mean absolute error? Hmm. Tell me.
So 2.60 or 2.49.
2.60, right? To 2.60 or 2.49 was something which was for single feature,
Okay.
right? When we just use a TB component,
Okay.
right? When we use TB and radio both, okay,
Mm.
our error came down to this was for the TB component. Uh, See, you said it right. When we use just TV component, it was 2.60 or something. But when we use TV and radio both, our error came down to 1.2 something, right?
Mm.
Anna? So now if you see, when I use non-linearity on the same data, it came down to 0.39. Okay. So it means that non-linearity is actually effective over here. Last time when we applied non-linearity only on TV component, okay, like here we applied the non-linearity on the TV component. Okay, here I just took what x is equals to TV, y is equals to sales. So when we applied the non-linearity on the TV component, my error didn't came down, right? It remained close to what? Where is the error? Have we calculated the error? Hmm. See, okay. So when we use the non-linearity only on the TV component, it was 2.5. The error was 2.5. But when we use the non-linearity on TV and radio both, okay, error came down drastically down, right? That means here non-linearity is effective. So non-linearity, when there is general question, when should we know that when to use non-linearity? When it is improving your model. Okay, here it is not improving your model. Here also we use non-linearity. You can see we use 3-degree non-linearity. And what we did, we use 3-degree non-linearity, right? But that 3-degree non-linearity is not improving your model, right? Model remains same, performance remains same, close to 2.5. So here we can't use it, right? So this model we can just disregard. We'll say that no, we can't use you, right? But this model we can accept because it is improving the performance. Understood? So what we did, we have a data, we just define x and y, perform the nonlinear transformation, and then we are using it, right? So can we use 3-degree? Yes, you can use 3-degree as well. Okay, but with the 3-degree, what happened? First of all, let me show you. With the 3-degree, here performance came, the accuracy or error came down slightly, but this guy, the number of features increased a lot. From 5 features, now we are having 9 features, right? So it's like you are increasing the size of your model, right? So if the size of your model will increase, then what will happen? It will take more resources to store. It will be slow, right? It take more time to process, right? So it's like, if you are increasing this thing degree, so you are increasing the number of coefficient that model can find. Okay, if model can find more number of coefficient, obviously it can be more accurate, but at the same time it will be expensive as well, right? It will take more resources to store, to process slow, right? So we need to check that if I am investing, if I'm going with the more resources, so how good is it? Is it improving too much or not? Like, like we have so many models like GPT-3, GPT-4, GPT-5. So why they are charging different? Okay, if you see the pricing list of GPTs, I'll show you here. I'll show you the pricing list actually, so that you can understand the difference between it, right? Here is a pricing. Okay, so why are they charging different? For GPT 4.1, it's $2 for 1 million token. This is for $0.40 for 1 million. So what is this token and all? I'll tell you when we discuss generative AI. This is 0.1 million token. So then this is expensive. This is cheaper. Why is it so? Because of the size of model. This is a very big size model. This is a small size model. This requires more space. This requires less space. This is very fast. This is slow, right? Or you can say this adds lesser parameter. Right, same way we have the linear model is small. Here non-linear model is big, right? It is having 5 coefficients. So kind of when we build the model, we can build different models. Okay, a small size model, big size model, mid size model, right? And we can just kind of create a comparison between them, right? Now it depends upon the person who wants to deploy it, that whether that client wants a big size model, can afford GPU, can afford huge amount of storage, right? Or we can go with a small size model, right? So now with the non-linearity, we had seen performance enhanced in this case, and it's a good enhancement. But now there is one more thing that we can try, okay, which is called feature interaction. Okay, so feature interaction can improve your process and it will not increase the model size also much. Okay, what is feature interaction? See, when we are using non-linearity, okay, we said that my model will calculate the output using this formula. If I have two features, okay, suppose I have these two features, right? So in that case, my model will do what? Will calculate the output using this particular formula, right? W1 x1 W2 W3 x1 square plus W4 x1 into x2 plus W5 x2 square. Using this formula, it will calculate. Okay. Then the difference between y and y hat will be calculated, which is your error. Now the optimizer will optimize it. Optimizer will optimize this particular error, right? Now the thing is, if this is the process going on, so it is using x1 to get trained and x2 get trained, right? Now here we are increasing the magnitude. We are making it x1 square, right? That means the feature value is suppose 259. So here we are using what? 259 square. That means a very big magnitude, a very large magnitude. Okay, problematic, right? So the process will automatically get slow. So we do what? We say that we don't want to use these two things. Okay, I just want three components over here to train my model. Y hat is equals to W0 plus W1 x1 plus W2 x2 plus W4 x1 into x2. This is called what? Feature interaction. Okay, feature interaction. If we implement the feature interaction during the training, okay, my model performance can increase and the size of the model will also not get affected much, because we are not using a square, cube, or that kind of thing. Okay, just multiplying two different features over here, right? So if I have to just use the feature interaction, let's say linear regression, sorry, non-linear regression using feature interaction. So it means what? It's not just about building up a model and saying that, oh, I built a machine. No, it's about tuning. So I'm trying to tell you the different tuning process, right? So let's say I have a data over here. Okay. Then we are doing what? We are just splitting this data. Okay. Then we are doing what? Transformation, polynomial transformation. So first step is what? We define feature and label, right? Second step is what? Split into train and test. And third step is what? Perform polynomial transformation. Okay, polynomial transformation. Okay, and use just feature interaction. Okay, so here what we do, from sklearn dot pre-processing import polynomial features, define the object, same step, nothing different. Okay, and then let's say degree 2, and next what we define apart from degree 2, we define over here include bias is equals to false, and last what we can define, feature interaction. If you see over here, there is a parameter over here, interaction only. Okay, interaction only. Okay, so I just want the interaction. I don't want that square, cube, anything. Right, I just want the interaction. So pol dot fit xtrain and then pol dot transform xtrain. So when I did it, what are we getting? We are getting over here x1. Just a minute. Here it's like we have a features like TV. This is radio, and this is a product of TV and radio. That's it. Okay. If you calculate to this one 2.8, 2.28 into 10 to the power 2. This is 3.7, 7 into 10 to the power 1. If you multiply these two things, you'll get this one. That's why you can say it is 10 to the power 3. Right? Because from here it is 10 to the power 2. This is okay. Here it is 10 to the power 2, here 10 to the power 1, right? And here it is what? 3. Right? That means 2.28 into 10 to the power 2 will be equals to what? 2, it can be 2.8, right? If 0 is also there. Okay? And here it can be what? 37.7 something or whatever. So if you multiply these two things, you'll get it. Right. So now this is a transformation on the train data. So X train, let's say feature interaction. Okay. Same way X test, feature interaction. So that POL dot transform X test. Okay. Thereafter we can do what? We can try in import from sklearn dot linear model, import linear regression. Okay. Then we can say model B is equals to linear regression. Okay. Then model B dot fit. Okay. I have to use feature this one, that is xtrain feature transform, comma xtest feature transform. Okay. So it's like, sorry, here I did it wrong. Okay. Here I have to give out y train. How I can use xtrain xtest over here? It's a xtrain and y train. Right. So now it's like once the model got trained. Okay. Here we did what? Train the model. Then we can do what? We can just model B dot predict. Now to make the prediction on what? Xtrain the new feature. So this can be your Y train predicted. Same way we can have the Y test predicted. Model B dot predict X test. Okay. So we have Y train predicted and Y test predicted both. Right. Now you can calculate the error. So mean absolute error on the train data, that can be equals to y train minus y train predicted. Y train minus y train predicted. So it will be what? Mean absolute error. MAE test, that would be equals to mean absolute error of y test minus y test predicted. Dot me, right? So now we will check the performance, okay, after the feature interaction. Okay, with the feature interaction, how is it performing? Right. So I'll just copy this thing, okay, and paste it over here for the quick code, right? And here I can just call what? Feature interaction. All right. So from 1.2, it came down to 0.63. Okay, it came down to what? 0.63. That is quite good. Okay, yeah. Previously it was 0.39, 0.4. Okay, it was 0. Close to 4. Here it is 0. Close to 6 or 7. But it is not such a huge difference that I can ignore this one. But the benefit of this model is what? This is being trained only on 3 components. Okay, as it is being trained on the 3 components, this model we can accept it to be more faster. Okay, see, here we are using very small size data, so you will not find very, you will find much difference in the performance speed and all, right? But here it's not about the small size data. I'm talking about the large scenario, that the actual kind of when we work on some very large project. Okay, then these kind of modifications actually very effective. Okay, we just try to reduce features. Feature selection is one of the most important part. It's not like that we have 100 features and we can all use 100 features. It's a very important task to analyze and choose the minimum number of feature to get the maximum possible accuracy. So this way we are getting it good. Okay, it's like if I use feature interaction, we are getting a good model over here. Am I clear? I'm sharing this file with you, and then I will tell you one more thing. Just a minute.
Sir,
Hmm.
sir, what is fit underscore transform?
Okay. कहाँ देखा आपने?
Sir, actually, I was studying. That's why I just
क्या हुआ?
asked. Sir, I was studying last night. That's
बता
why I
दूंगा.
just.
Right. Good. So that is very important, right? I recommend everyone to apart from what I am covering, please just try to go through some other code, other resources, Kaggle, GitHub, right? Because it's not like that I will cover A to Z. Obviously, I'll cover majority of the thing, but no one is perfect, right? It may be possible some of the things I'll miss. But when you ask me, it will help you to learn. Like you asked me what is fit underscore transform. What happened? Here I did it in 2 steps. Okay, I fit over here and then I am transforming. Okay, so if I don't want to do it this way, I can directly do over here fit underscore transform. Right. That means, let's say if this is the thing, okay, and we define this one, then if I use pol dot fit underscore transform, okay, so it is doing the fit and transform at the same time. Okay, like here fit is doing what? Fit basically let this algorithm know that we are going to give you 2 features. Okay, it let this algorithm know that we are going to give you 2 features, right? That you have to transform according to 2 degree. Okay, so 2 degree transformation of 2 features are like this. So into x2 and then x2 square. Right. So if I have to do the 2 degree transformation, I am giving you this thing, just do it. So next, it is like informing, and this guy is actually transforming. Okay, this guy is just informed this thing that I'm going to give you 2 features because x train is having 2 features. right? Now this guy is actually transforming, and after transforming, we are storing the output over here. That means fit is not returning anything, right? If I just use fit over here, it is not returning anything. Okay, it just defines that what is going to happen. But if I use fit underscore transform, so it will fit as well as it will return the transformed data. Okay, so it is like this, right? But after this, the next time when you are using the transform, like see, whatever the rule that extern is following, okay, whatever the rule extern is following, you have to use the same rule for test, right? It's not like that you can use any other rule for test. So pol dot transform, for the test you don't have to use fit. For the test you have to just use transform, right? So it is like this. Okay, so it is just combining these two things into one. That is called fit underscore transform. All right. Is it fine?
Yes, sir.
Mhm. Okay. So now the performance actually is good. Now, there is one more matrix actually, whenever you are working on, linear regression kind of thing, it is important to evaluate mean absolute error. But apart from mean absolute error, we should also evaluate one more thing, which is called your R2 score value. Okay. There is one more component that we should evaluate, which is called your R2 score value. Now why we should evaluate R2 score value? To make you understand this part, let me try to take data for you. Just wait a minute. All right. Mm. All right, let's try to take this data. Okay, this will also help us to work on a project, right? So let's see, because if I directly explain R2 score value, you may forget that, but I don't want you to forget it. That's why I want to give you the relevance of that as well. So for that, I need one more project, because on this project, if I explain, you may not find the exact relevance of that. Import pandas as PD, import numpy, import matplotlib dot pyplot as plt. df is equals to pd dot read underscore csv df dot head. I'm saying this file link also with you in the chat. So now when I'm accessing this data, so this data is having what? Some of the informations like item identifier, wave item weight, item fat content, item visibility, item type, item MRP. So these are the informations related to items. Okay. And then we have some other information. These are the informations related to outlet. Okay. That means where the item is placed. And then we have a sales value. So ultimately, let's suppose you get this data and you have to analyze, pre-process, and then build the predictive model. Okay, analyze, pre-process, and then at the end you have to build the predictive model. Fair enough? So what would be your approach? How do you start? First thing, it's like we check the shape of this data. Okay. Second thing, we check the types. Okay. Like, okay, what are the things that, like, we have numerical, non-numerical kind of things, right? Third thing, we'll check over here the number of unique values, so that we can get a general idea that which column can be considered as categorical. Okay, this is a categorical. Okay, this is also the other thing. So I guess this data I had used earlier with you, right? I'm not sure, but I'm getting a feeling like I had used this data with you. Anyway, if I've used, that's fine. If I'm not used, then also it's fine. It will be a division for you. So now we get over here the unique values and all over here. Okay, it represents that, okay, these are the categorical column, these are the something like that, right? Next, what we do, we have kind of a okay. Next, we'll try to find out the missing values. Yeah, I had used it with you. I had used it, so I'll just do it quickly. Okay, so that it can be a good revision also.
You used in the pandas section.
Right, I had you. Now I can recall. Okay, so these are the things we did. Right. So once we did this thing, okay, in which file I had used it? Let me just try to pick that thing. Session 4, session 8, and session 1. Okay, here I had used it, right? Statistics. Yes, here I had used it. Okay. So I'll just give I'll just do it quickly because now I have to implement it for the machine learning. So I'll not take that much time that we did earlier. Right. So, now here it's like we have the missing values. Next, what I did over here, identify the unique values, right? Thereafter, it's like identify the numerical and non-numerical columns. Okay. So here I have a numerical columns and non-numerical columns so that we can say that what are the numerical and what are the non-numericals, right? And we can analyze them separately. So now with the non-numerical columns, okay, how it's like how to select df dot select d types. Okay, select d types, exclude number or include number. So here we're excluding the number, so only non-numerical. If I use include the number, then only numerical. Right. So with the non-numerical, we find that, okay, here we have some categorical columns. Next, here we identified that in the fat content column, we have 5 categories that we converted into 2 categories, right? So for converting a 5 categories into 2 categories, what we did, we created a function, right? This function is doing what? It is just capturing the fat content information and returning low fat or regular, right? So it's like when I apply this function on the given data column, that data column now will have only 2 categories, and those 2 categories will be what? Okay, those 2 categories over here, dot unique. All right, low fat and regular, right? Now we have over here the non-numerical columns again. So we just converted low fat, LF and other things into like that. So okay, so here I can't, because here I'm not separating non-numerical columns, so I can't use it. Now you have the item types, identified unique values in item types. This is also working good, no problem in it. Thereafter, we identified the value counts in item type just to identify if there is any outliers, no problem in it. Okay. Thereafter, we went to the outlet identifier. Here also we don't have any issues. Okay. Thereafter, we went to outlet size, small, medium, large, no problem in it. Okay, we have 3 outlet size over here. Then outlet location type. We have 3 outlet location types. All right. Thereafter, we have outlet type. We have 4 outlet types. Okay. Thereafter, we have item identifier. Now, when we went to item identifier, here we get the fact that we have so many unique values. So if I will go with this thing, my model will not get the information about each category properly. For some of the category, it will get the very less info. All of the category, it will get the very less information, right? Because the value counts. If you check it over here, none of them are having more than 10 samples. Okay. Okay. So that's why we need to do what? We just pick the first 2 characters from here. Okay. So here we are just picking up first. We created a function, okay, like this, which will be responsible to take the first two characters. What are those first two characters? FD, DN, or RC. So function is item identifier that I have created here. Okay. This function is responsible for what? It will take the value from any cell and return first 2 character, right? So I'll not create this function separately now. I can directly create this function within this bracket itself. Okay, this is also fine. We don't have to define the function separately. All right. So this makes sure that your now data is modified with FD, drink, and NC. All right. Now we have this thing is done. Now again we check the unique values. Number of unique values. All right, this is also fine. Next we did what? We identified the null values. Okay, so now I have 2 null values, one in the numerical column, other in the non-numerical column. Okay, so I told you the process of handling those kind of null values. So first we handle over here for the non-numerical columns. Okay, so we have the null values in the outlet size, right? We have the outlet size, we have a null values. So you can see in this thing we have 2 sections of the data. The one section is item, okay, the other section is outlet. So we have a null value in the item section, we have a null value in outlet section, right? So what do? We just take over here the outlet part first, okay, df of outlet size. So here we have 3 things, okay, medium, small, and high. All right. So it's like we can do what? We can, wherever the missing values are there, I can replace those missing values with the medium. Okay, we can just replace all the missing values with what? With the medium, but that will create the bias data. We don't want to create the bias data. So what we do over here? We will count this thing. That means we will work on this kind of column. Okay, we'll try to find out how location type is related to outlet size. Okay, how location type is related to outlet size, that is outlet location type. Okay, how outlet location type is related to outlet size, or how. So we identified this thing using crosstab. It's a multivariate analysis. Okay, so we find the information that what is missing. The missing value is outlet size. Okay, we have outlet size is missing. Outlet size is missing. Okay, as it is missing, we find that if it is a tier 1 city, okay, so most of them are small. For tier 2 city, all of them are small, right? For tier 3 city, most of them are medium. So we get an idea. Wherever it is missing, and it is tier 1 or tier 2, replace with a small. Okay, and wherever it is missing, it is tier 3, replace with what? Medium. Right. Now, why I used only this thing, that is your outlet location type? Because when I analyze the outlet type, okay, because this kind of relation we can also find out with outlet type. Okay, This kind of relation we can also find out with the outlet type. But problem with the outlet type is what? Outlet type is biased. You can see most of the outlet type is supermarket one. So this biasness I don't want to use, right? That's why we created a function over here. Okay, here. Okay, this function is doing what? This function will check outlet location type. If it is tier 1 or tier 2, it will return a small, otherwise it will return medium. Okay, so this is how someone will create a function. Okay, this is how someone will create a function if the person is, kind of a beginner. Okay, if you are experienced, then I'll tell you how to do this thing. Same function will create using lambda. No need to write a separate function. Okay, here we'll write what's lambda. Lambda outlet location type OLT. I'll take a parameter argument called OLT. Now we will return a small. What I want to return, I'll write it over here. So this lambda function is being created to return a small. It will always return a small. Okay, whatever the things happen, okay, in this world, right? It will always return a small, right? So now if OLT in, now I'll write a condition. Now it is being limited. Now it will always return a small if OLT, that is if outlet location type we give is tier 1 or tier 2. Else this guy will return what? Medium. Okay, so we created a lambda function, right? So this lambda function can help me. So if we create a lambda function, then how to use it? Very simple. Okay, here we'll take the, see, everything we did we'll do in a single line, because now it's time to upgrade yourself. Okay, so now we have an outlet location type column, and in that column we have to apply this particular function. So just copy this function and just put it over here. So instead of creating a function separately, then applying it, then filling it, okay, just one line of code. Okay, so try now, just try to start writing this kind of a script. Okay, trust me, if you want to switch, if you want to get good opportunities, okay, at this stage, now you need to upgrade yourself with this kind of a scripting as well. Yeah, it will take time, but slowly we have to start. Okay, by doing the errors, by doing mistakes, correcting it, asking from me. Okay, so that's how we have to move to this kind of scripting. It's because most of the time, like everyone knows that what is function. Okay, function everyone knows. Okay, so no one will like in the interview, you will don't expect that anyone will ask you that tell me about Python function, right? They will ask you the questions like what is lambda function, what is list comprehension, okay, how you can, or you can say what is your default parameter, default arguments, right? Where can you put the default arguments, right? Or you can say what are variable length arguments, okay, what are variable length keyword arguments. These things I have explained you, right? But don't worry, I'll take a separate session for you in which I'll try that I'll cover some of the very tricky interview questions and with the answer, so that it can help you. But anyway, let it be that I'll cover for you. As of now, let's start with this thing. So it did what? It just checked the outlet location type and had given the value as a small or medium for each sample. But I don't have to affect each sample. I have to do what? I have to affect only the missing values, because I have the information for all the samples. Why should I affect all the sample? Okay, all the samples are having medium and small, so only I have to affect this guy, isn't it? So over here, this thing we can use outlet size based on outlet location type. Okay, outlet size based on what? Outlet location type. Now we will do what? Outlet size, df of outlet size dot fill na, this guy. Okay, and then your outlet size will get updated. Done. Right. So df dot. So how many lines of code I write? I write over here just 2 lines of code. Okay. Over here we just write over here 2 lines of code. Okay. One line to identify, other line to do this thing. Even I don't prefer it writing in 2 lines. Okay. I prefer it writing in just single line. That means, you know, this thing I just put over here. This whole thing I put over here. If I can write in a single line, then why I should go for multiple line? Because, you know, always I want to show you that why single line of code is actually good. Just a minute. For showing you, I need over here. Okay. Let's show you. So that, you know, if you know it should. I just want that it should keep with you, so you can keep with you for longer duration. Okay, so for that, I don't want to disturb this particular code. Let me create a new code actually. I'll show you that the actual effect I want to show you, right? Just allow me for a minute. That the normal coding and the lambda function, because, you know, it's not that theoretically you should know. You should see like what is the actual effect. Patterns, speed. Okay. So now I'll create 2 data frames, df1, okay, and df2. So that I can use 2 different processes over here. Okay, in df1 and df2, I want to use 2 different processes. Both are having the missing values, right? Now what we do? Okay, so here there is one function. Okay, all right. This is a normal function, and here it is a lambda function. Okay, and this will also I define as fill outlet size. Okay, both the functions, both are there for same purpose. Okay, just written in 2 different ways, right? Now what I'll do, I'll just import over here a module called time module. Okay, now this time is having something called, just a minute, time dot I want over here. Actually, Unix time I want. So for Unix time, there is a method that I am just missing over here. Just a minute, let me check. I want a Unix time, so there is a method for that, but I'm just missing that particular method. So I have to check it using help. I can check. Static TM offset from UTC in second. Okay, TM hour, TM this one, TM method. Sky time, string, get time, nanosecond, convert time, GM time, local time, but it will give you something actual time, process STRF time. What is Unix time, thread time? This line for me, I just check and delete it, you know. It's example count. That's difficult. So I'll do what? Time module Python Unix time. I know there is a method, but that method I just missed because okay, it's very simple. Dot time. Oh my God, what I'm doing? time. Let me just comment it. Okay, so here I do time dot time. Okay, so I got a Unix time, right? So now what I do, I'll take this time dot time, let's say start time. Okay, start time is equals to what? Time dot time. It will just calculate the time. Then what I do, I'll take this data that is df1. Okay, and then I'll take over here the column, which column? Outlet size dot apply. Okay, and what I apply? I'll apply this guy, this one, the first function. Okay, I'm applying the first function, that is your normal function. Okay, so it will do what? It will check. Sorry, I have to apply it on outlet size or outlet this one, outlet location type. Okay, I have to apply it on the outlet location type. I did a mistake because it will check the outlet location type, right? It will check the outlet location type from here, isn't it? It will check the outlet location type. If it is tier 1, tier 3, it will return what? Small. Otherwise, it will return what? Medium. So this is start time. And thereafter, let's say I will over here make it end time. Okay. And then I'll calculate the time. Okay. Time takes. So what is over here time it is taking? It is taking the time as start time minus end time. Okay, so it took over here. Okay, so here I should use end time minus start time because end time is bigger, right? Okay, right? So it's take around 0.002 seconds, something like that. I'll take df2. All right. Now in the df2, what I do, I'll apply the second one, that is a lambda function. Because here the almost same it is giving the result. Okay. Here it is not. I thought like it will give you the different, slightly difference, but this data is not quite enough to. Okay. 0.224, somewhat almost same result it is giving you. To 0.02. It is actually this data is not giving us a situation where I can, but actually I thought like it will give us some different result, but you know this size of data is not quite enough to give you the actual kind of a scenario. Okay, let me show you in different way actually. Let me just increase the data size, right? So let's say I'll create a function over here. Okay, or okay, let's say over here. Let's say for I in range, okay, 0, 1 million. Okay, 1 million. Okay, let it be 1 million. Suppose you're working on 1 million data, right? Now what I do, I will store over here, store, or you can say value, list of values. Okay, this is what, this is kind of a list, right? So in this list, I want to store dot append I. So I want to store this value. Fair enough, right? Now I do the same thing. Start time and end time. Okay. This is just 10,000, I guess 8 or 7,000 data is there. That's why I'm not getting a major difference. Okay. Now it is taking what, 0.9 second approximately. Right. Now what I do, I'll take the same thing. Okay. And I'll make the change over here. Okay. This loop I'll remove from here. Okay. And here I'll modify this code using list comprehensive. I'll write over here what I, okay, for I in range, okay, for I in range 0 to 1 million. This is 1 million. Okay, so it's like same thing. Okay, whatever we are doing over here, we are doing the same thing over here. Okay, it's like here we are just running a loop for 1 million time, and when I am running a loop for 1 million time, I am just storing that value into this particular list. Running a loop for 1 million time is storing the value in this list. Here also you're doing the same thing. Here the value of I will store, value of I will store when this loop will run for 1 million time. All right. So you can see the difference. It's 0.09 seconds, 0.04 second, lesser than half, almost half, right? Even lesser than half, you can say, almost, yeah, right? So, this thing actually effective. Okay, it is actually effective when we use lambda function or when we use one line of scripting, right? Using list comprehension and all. Here also, I thought like it will show some difference, but here, it may be your size of data is not that much that it will show you the major difference. Okay, that's why it is not showing you much difference over here, almost very close with 8,000. Because here also, if I suppose use only 10,000 samples, okay, suppose 10,000, then here also I'll not get a major difference. Okay, almost it is same kind of thing, right? So it depends upon when we actually work on the very large data, then we actually get the difference, right? Okay, so here if I'm working on 10 million data, 10 million sample, you can see the change, right? So that's why I said like try to write the code in this way, okay? Because as of now you may not find a kind of a major difference. You say that why if this is better, okay? It is easy to understand. This is also later on you'll find this is also more easy to understand, okay? But when we work on the larger scale data, this will be effective. So we fill up all the missing values over here. Next, what we did, we identified the numerical data over here. So in the numerical data, we have the missing values. We just did some sort of outlier check, okay, and we just try to fix those outliers and all. Okay, so as of now, I'll not do that. I'll just use them as it is. Those outliers fix you can do later on, right? Or after model building, I'll try to fix that. But as of now, I'll just keep them as it is. Okay, I'll directly fill the missing values, right? So I have a missing values in the item weight, right? So I'll fill the missing value in the item weight with the average value because that is a numerical column. So I'll just take the average value df of item weight dot fill na. I'm not giving any outlier treatment right now. Okay, I'll build the model without outlier treatment, and later on I'll do the outlier treatment and we'll see that if there is any major effect. Okay, here I'm directly filling up the missing values in weight. Here I didn't fill it. Okay, previously I didn't fill it directly. Previously I did what? I did over a grouping, identified the item weight for each item type. Okay, identified the item weight for each item type, and then we created a function, the function which can take your item type and return the corresponding item weight. This function is taking your item type and returning the corresponding item weight. Right? Like I had given soft drink, so it returned this one. So this function we had applied on the item type data column, right? So that the function can take your item type and return the corresponding average item weight. Okay, it will return the corresponding average item weight from this table because this table is representing average item weight of each item type. Average item weight of each item type. So the function is doing what? This function is looking at this table and returning the average item weight of an item type that you give. So we applied it on the item type column, we get it, and this particular value we use in the fill in. So here we are filling considering the item type, but most of the value are very close to 12. Okay, and overall average value is also 12. If you check over here, 12.7 or something like that. 12.8, right? So here we are just filling up the value, right? So it can be your item weight. All right, that is done. Then let's check the null value. No null values. Now my data is almost ready. Okay. Here we just left it right. So here we have a data ready, and this data we are going to use it for the machine learning purpose. Okay. Only we have to do what? Few changes we have to do. Like here we have to convert the non-numerical columns into numerical. And once we convert the non-numerical into numerical, we can use it for the linear regression model building. So next step, we are going to use it for building up the linear regression model, which can be used for predicting the sales value. All right. So let's do this thing. Before I'll go ahead, we'll take a short break. Meanwhile, I'll share this file with you. Right. We'll just have a short break, and after the break, we'll finish it. All right. Is it fine?
Yes, sir.
All right. So just short break. In just 5 minutes, I'll be back. Or you can join back by 11:25. It's okay. 11:25, we can join. Hi everyone. Sorry, I just got stuck. There was some call. So let's proceed. So what do we have? We have a data prepared. We have to use it for the ML. So one more thing we have to do is like we have to convert these non-numerical columns into numerical. I'll create a df1 is equals to df dot copy. Mhm. Okay. Just 1 minute. All right. So I just created a copy of this guy. Right. Next, what we do here, we know the first column is item identifier. So I'll just check those columns which are non-numerical. Right. So we can just have a data columns like say df1 dot select d types. Okay. Include, or you can say exclude, is equals to number. So these are all your non-numerical columns, right? I can just get the column names from here, dot columns, okay, dot to list. So I have a list of those data columns which are non-numerical. Now I'll try to process each one of them one by one. Let's say first take item identifier. Okay, or I can see over here non-numerical columns. COLUMNS. Okay. So we have identified the non-numerical columns as a list. Right. Now I will try to go through these each column one by one. So for column in non-numerical columns. Okay. Take DF from the data frame or DF1. Okay. From the data frame, take each column one by one. Dot unique. Okay, that means it will help me identify the unique values from each data column. Right. So we can see that for the first I have these unique values, then we have this. So now I have to convert into numerical form. So to convert into numerical form, there are two ways. Okay. That means one is called label encoding. Okay. And other is called one-hot encoding. Okay. So when do we perform label encoding? Can anyone tell me? I told you earlier.
For categorical data.
Mm-hmm.
For categorical data.
You're right. It will be for both are for the categorical data. Label encoding we perform on the if it is just two category. Okay. Wherever we have two category, we can do that, or we can do it for the ordinal data. Can anyone tell me what is ordinal data? Which we can put in a order like this: small, medium, and high. Again, so small is over here is what? 0. This is what 1. This is what 2. Right. So it's like small, medium, and high will represent your ordinal data. It will just represent your ordinal data. All right. And what is nominal data? Do you understand what is ordinal data? Ordinal data is something which we can put in the order, and if it is in order, we can assign them the numerical value also in the order. Okay, and these are what nominal data that we can't put into order. So for nominal data, what we do? One-hot encoding. All right. So let's try to perform over here. First, label encoding for ordinal data. Okay. So it's like DF1. Let's say the data column is what? Item fat content. Dot map. Okay. What we map? Let's say take this thing. Okay. I can make it 0. I can make it 1. Right. So here this will be converted into numerical form. Okay. Next, this is multiple category, but it is nominal. This is what we can just remove this first 4 character. It will automatically become numerical. If I remove first 4 character, it will be numerical. This is also ordinal. That means outlet size. So I'll take over DF1. Outlet size. Dot map. small, medium, and high. Small, 0, medium, 1, high, 2. Okay. So we did it. Right. Tier 1, 2, 3 also kind of ordinal, only it is in order. Right. So we can do what? We can just take over TF location type. Dot map one, 3, 2. Okay. So I'll just put it like this. Okay. Rest we can do what? One hot encoding. Okay, so df1 dot head. Right. So, what happened? I have not executed it. Oh no. Okay. So now it is converted into this thing, right? Now left out with, we'll work on these guys. But before that, let's fix this thing. Because here we'll do what? I have to just remove first 4 characters. So what I do? Can you just help me? How can you do it? I have over here df1 outlet identifier. Okay. And I want over here only last 2 characters. So what program, what should I write? What should I write? See, already we did it here. Here we captured the first 2 characters. Now I want to capture the last 2 characters because last 2 characters are numerical. Can you help me please? Just look at the code that we did earlier and please try to do this thing. Let me know. Just think of it. It can take 2 minutes. No worry.
Colon minus 2.
Yeah.
Colon minus 2.
Right. We can do what? Just we can take the last 2 columns. Just a minute. So the last 2 characters, right? Right. So it's like, let's say I have this thing. Text is equals to this thing, right? So if I will use text -1, so it will give me what? Last character, that is 9, -2. It will give me second last character. From second last character, everything. And then I have to convert this thing into integer. Then this is what I have to do. So what I do, I'll just take this column. Okay. Dot apply lambda x, that is your function. And this function should be applied on each particular value. So x -2 colon. So when it will be applied on each particular value, you can see what I am getting. Because, I have to apply the same process on each data value. So this is what we are doing. Okay. So now df1 dot head. So now it is just done. All right. Okay. Now I am left out with few more columns. Okay. So whatever the columns I'm left out, now I have to do the one hot encoding. So it's like one hot encoding for nominal data. Nominal data columns. Okay. So for that, we can use pd dot get underscore dummies. Okay, and feed df1 here. So it will automatically convert the non-numerical columns if you see into one hot encoding. True false is what? 0, 0 and 1. Okay, I can just take over here data type is equals to integer. Okay, so what is one hot encoding? You know, if I have over here food, drink, and non-consumables, okay, like this. Okay, so I have three categories, right? In the item identifier, I have three categories: food, drink, and non-consumable. So food is being labeled as 100, drink is 010, and non-consumable is 001. So here we have 010. So that means this must be drink. This sample must be drink. Here I am getting 100. That means this must be food. All right, you can check it. This is the first one I am getting over here. Okay, so here food is 010. Okay, fine. It is little different. Okay, so it is like this. Here we have, here it did what? Drink has been given as 100, food has been given as 010, and non-consumable has been given as 00 based on alphabetical order actually. Alphabetical order is used. So it is what? 010. That means it's a food. Drink 100. It's drink, right? So accordingly, it is being given. I can store your df2. All right. Now we have what? One small change I'll do. This year is numerical, but its magnitude is huge. Its magnitude is large, like 1997, 1998, 2000. So instead of this year, what I can do, I can make it age, right? So I can use 2025 minus df2, that particular column. Right? So I get over here the age. Okay. So now df2 dot head. Okay. So you get the age of that particular data column. All right. So now my model data is completely ready. I have to build model which can predict the sales. Okay. So for this process, now let's work on the machine learning model. So for that, x is equals to df2 dot drop columns is equals to, and then y is equals to df2. All right. Now from sklearn dot model selection, import train test split x train, x test, y train, and y test. That would be equals to what? Train test split x comma y. All right. Thereafter, from sklearn dot linear model, import linear regression. Model building is the most easiest thing. That means it happens at the end, and it's just the 30% of your whole process. Model A dot fit x train comma y train. All right. Now what we do? Evaluate. So y train prediction is equals to what? Model A dot predict x train, and y test prediction is equals to what? Model A dot predict x test. So my predictions are made. I have to calculate the error. So Y train, that is your actual sales minus the predicted sales. Okay, we get positive and negative differences. Let's take the absolute value of it. Okay, so this is what mean absolute error on the train data. Okay, thereafter, let's say mean absolute error on the test data. Okay, now I just print both of them. Mean absolute error on the train, that would be what? MAE train. Okay, and then mean absolute error on the test. Okay, thereafter we can use it as a formatted text. F. All right, so your mean absolute error coming out to be close to 830 or 840. Okay, that means while predicting the sales value, the average error that my model may have will be close to 840. Okay, while predicting the sales value most of the time. Right. Now here, the last time we build a model on advertisement data, okay, last time that we build a model on the advertisement data, right, that was giving me the error value 0.6 or 75, and here it was giving you the error close to 0.3, but here I am getting an error, this one. So this error is what? It totally depends upon the target value. Okay, it depends upon what? The target value, right? If the magnitude of target value will be kind of larger, the average error will also be larger. Okay, if the magnitude of target value is lesser, the average error will also be lesser, right? Am I clear? This average error depends upon it. Totally depends upon this particular entity. Here it is larger, that's why I'm getting it larger. Here I am getting, here we have a sales value is smaller. That's why I'm getting it is smaller. So how can we trust? How can we decide that which average error is acceptable, which is not acceptable? Right? Because there is no threshold. Okay, it is not like that it should be 500, it should be 1, it should be 2, it should be 3. There is no threshold. Overall, it's not normalized. Okay, it is not normalized that we can say that, okay, this is acceptable or this is not acceptable. That's why we need what? One more matrix for evaluating this thing, which is called R2 score. Okay, this is a formula for R2 score. In the regression, we use it. Okay, what we use? R2 score. Right, now what R2 score does? See over here. It is calculating the difference between the real and the predicted value. Y is what? Y can be your real sales, and Y hat is what? Predicted sales. Okay, so this is a normal error. Okay, this is what the normal error that we are calculating is just taking the square of it. All right, so let's do it. Step by step we'll do it. Here I have the Y train minus Y train predicted. We take this thing. Okay, and then we take the square of it. Okay, so here what we got, and then we also take this sum of it. We also take what? Sum of it. Step by step we'll go. So let's take the sum of it. Done. Nice. Now this is what, are you getting any information from here? No. Here we are just calculating the difference or sum of a square of differences between real sales and predicted sales. All right. Okay. Now we calculate the difference between Y train and the average of Y train. Okay, we calculate the difference between Y train and average of Y train. And then we take the square of it. And then we calculate the sum of it. Okay. So this is giving me what? Sum of a square of differences between given label and average of given labels. All right. So why are we doing this? See, let's try to understand this thing here. I have something called Y. Okay. Let it be 3, 5, 7, 9, 2. Then I have Y predicted. Let it be, let's say 5, 8, 4, 4, 4. Let's say 5. Too many 4s are there. All right. So we will calculate two things. Y minus Y hat. What is Y minus Y hat? This is minus 2. This is minus 3. This is 3. This is 5. This is 3. We take the square of it. Y minus Y hat square. Okay. 4, 9, 9, 25, 9. Okay. And we also calculate the square between Y minus Y bar. Okay. So what is Y bar over here? 3 plus 5 plus 7 plus 9 plus 2 divided by 5. So this will be equals to 15, 15, and this is what? 15, and this is what? 11. 26, right? Let me decrease one value so that it can be 5. Okay, let it be, let's say I'll make it 4. Okay, if I'll make it 4, sorry. Okay, let it be 4. So 4 minus 8 will be what? Minus 4. Okay.
Mean is 5.
4 minus 8 will be what? Minus 4, right?
Yeah.
So 4 into 4, it will be 16, right?
16.
Okay. Yes, right. So here we did what? 3, 4. Just
5.
for make the calculations easy. So now it is 7 plus 3, 10, 10, 14, 14 plus 11, 25, right? So 25 by 5, that is equal to 5, right? So 3 minus 5, okay? 3 minus 5 will be minus 2, and 2 into 2, 4. Okay. 4 minus 5, 1. 7 minus 5, it is 2. 2 into 2, 4. 9 minus 5, 4. 4 into 4, 16. Okay. 2 minus 5, 3. 3 into 3, 9. Right. So we just compare over here the difference between the real and predicted value. Okay, we just compare what the difference between the real and predicted value with respect to the difference between real and its own average. Okay, with respect to difference between the real and its own average. This is a real and predicted value and difference between real and its own average. Right. So when we take the sum of it, okay, so it would be what? 16 plus 4, 20, 20 plus 25, it is 45. 45 plus 18. 45 plus 18 is what? 65, 63. Okay. 63 divided by 4 plus 4, 8, 1, 9, 9 and 18. 18 plus 16 is 34. Right. So it shows that compared to its own average, this particular difference is way higher. Okay. compared to its own average, this particular difference is way higher. So if you calculate it, 63 divided by 34, 63 divided by 34, what did it be? 63 divided by 34, it would be 1.85. Okay, that means now R2 score value, R2 score value will be equals to what? 1 minus 1.85. That would be equals to minus 85, minus 8, minus 0.85. Okay, so if it is negative, it means the model is not a good model at all. Okay, if it is negative, it means what? The model is having the way higher difference from its predicted value compared to its own average. Okay, the sales average, the difference between sales and its average is lesser compared to its predicted value and its sales, right? So it is not acceptable. Okay, so negative R2 score is a very poor model. Now comes to positive, right? So when it will be positive, when this difference will be lesser. Let's say here the predicted value. Okay. Let's say the predicted value here over here, let's say 2, it's like 5, it's like, let's say 11 or 10, it is like 3. So here 3 minus 2 it is 1, 4 minus 2 4, 4 minus 2 22 4, 7 minus 5 it is 2 22 4, 9 minus 10 1, 3 minus 2 1, right? Now if I calculate it, okay, it is a square. Sorry, here I just did it like this. So 4 minus 2 it's 2, 7 minus 5 also it's 2, it is minus 1, minus 1. Okay, so okay, fine. So it is 1 4 4 1 1. So 4 1 4 4 8 to 10 11. So now it will be 11 by 34. Okay, so what is 11 by 34? That is 0.32. Okay, now if you calculate R2 score, it is 1 minus 0.32. That would be equals to what? 0.68. Okay, so when this guy came closer to your actual label, when this guy came closer to what? The predicted value, when it is closer to the actual label for each sample, overall R2 score value becomes what? Positive. And it goes close to 1. So R2 score value can be maximum 1 and can be minimum, it can be negative, any value negative. But we accept it to be at least positive and it should be closer to 1, that would be good. Okay, R2 score value should be what? At least it should be positive. In any case, right? If it is positive, it means what? It represents, if R2 score value is positive, it represents what? It represents that the difference between real and predicted value is lesser compared to its own average value. Am I clear?
So can we say that if R naught square value is positive or it is close to 1, so the model will be acceptable?
Correct.
Just, okay.
Correct. Absolutely right. Okay, absolutely. You are on the right track, right? So this is what we are doing, right? So let's try to implement it over here. So it's like, this is your numerator. Okay. This one is denominator. Okay. Once we divide it, R2 score is equals to 1 minus numerator upon denominator. It is positive and it is 0.56. That means it is good. It is not that bad. It is good. We will improve it. We can directly actually calculate it from sklearn dot matrix import R2 scope. Now print R2 scope for training data is R2 scope, and you have to feed two things over here. The train in predicted value it will calculate, and then R2 scope for the test data. Sorry, it's comma we have to give. Okay, same value I am getting here, right? So that's why I told you that I want to tell you the R2 score thing, but with other examples, so that you can understand that why it is required. Okay, same way if I want to calculate R2 score over here, like in the advertising one, right? So let's say, okay, so here also we have to compare. So same thing we can do. Okay, so we have R2 score is coming out 0.96, which is good. Okay, when I used, okay, here what we used print using only feature interaction. What we used here? We used only the feature interaction. Okay, and then we will also implement it without feature interaction. That means on the over here when we got 0. So here using full non-linear transform data. So when I use full non-linear transform data, it is 0.98 and 0.99. Okay, almost close to 1. Okay, and here it is 0.96, but it is not bad. Okay, it is also good. Okay, considering that we are using lesser number of little lesser features, like those square term is not using, but our model is lighter in weight, will work faster. Okay, so R2 score basically help us to decide whether a model is good or not good. Most of the time we'll get the value between 0.7 to 0.8. Most of the time here we are getting 0.9 because this data is too good. This is not an actual, in reality you will not get such a good data. Okay, that is just kind of a thing, but here most of this is more realistic value. All right. Am I clear?
Yes, sir. Sir, one small doubt.
Tell me.
Yeah, can we use hypothesis testing also for model prediction? H0, H1 or p-value?
See, hypothesis testing is something that we don't use for model prediction. That we actually use for for interpreting some result. That is a statistical process. That is called a statistical analysis.
Okay.
Okay, hypothesis testing is not for prediction. That is the analyzing the data. Okay, like suppose it's like suppose you are running a company, right? Now you are making some expense on the advertisement. Okay, now after 6 months, okay, you did what? You decided that you will increase that thing. That is what kind of for the advertisement cost. Now you have to analyze that whether the increment in your advertisement cost is actually affecting your sales or not. Okay, so in those cases we do hypothesis testing,
Okay.
right? Like for example, if suppose there is a company who is manufacturing vaccine, okay, now the company wants to analyze or understand whether vaccine is effective or not effective.
Okay.
So they do what? Hypothesis testing.
Okay.
Right. So hypothesis testing is not about prediction. Hypothesis testing is about analyzing and concluding a result. Just make some conclusion.
Okay.
Right. So I'll do it for you. I'll cover the hypothesis testing part for you. Okay. Once we finish up this concepts, because I know when to put this particular information, because there are certain things that you should know. If you know these things, right? So it will be better. Like you can better understand hypothesis testing.
Okay.
Right? So I'll tell you. If I miss, you can let me know. Right? But I'll tell you about hypothesis testing, right? Don't worry. Clear?
Yes, sir.
Okay. So now let's talk about like how can we make these guys better. Okay. So let's talk about the sales, right? Now, what is the sales we have? We have this is a sales, right? Tier 2 item outlet sales. Dot plot dot histogram. Okay. So this is what? This is a right skewed data. I told you if the data is right skewed, then you have to convert it into bell curve or you have to convert it into a kind of a normal distribution. What should I do? Log transformation, right? So if I will take over here np.log, okay, and I take this thing and then I plot it plot histogram. It is little normally transformed. Now question is, will it affect your model? Let's check. YT is equals to the log transformed value. I want to use what? Log transformed value of sales. All right. So if I want to use a log transformed value of sales, what am I getting? Mean absolute error will come down because magnitude will be reduced after log transformation, but I have to look for R2 score. Improved from 0.56 goes to 0.7. That's a huge improvement, right? So we can say that if the target column is normally distributed or it is having a kind of a uniform distribution or Gaussian distribution. This is also called Gaussian distribution. It is not completely Gaussian distribution, but very close to that. So if a target column is having a Gaussian distribution or normal distribution, we can expect a better performance. Am I clear? Next thing, let's talk about the coefficient. Okay. So what I do, I'll just take over here model A dot coefficient. Because coefficient can help us to understand how each features are effective. Okay. So this is a coefficient that I can convert into data frame. Now what are we trying to do? We are trying to do the coefficient analysis. Okay. Let's convert into data frame, and here what we'll do. coefficient, model coefficient analysis to interpret the result. Okay. Here it's like we are trying to analyze the coefficient, right? So now I have one more thing that is called x dot columns. So these are the coefficient for each columns we have. Okay. So I can do what? Let's say coefficient, or you can say model coefficient, and then I can assign it model coefficient dot index. Okay, model coefficient dot index will be equals to okay this guys. Okay, so model coefficient I'll tell you what to do next. Just 1 minute. Huh? Okay. So the point over is we have a coefficient. Now what to do with this coefficient? Let's see. I'll take it and I will just plot it. Dot plot dot bar. So when I plot this guy, I get an understanding about each column. Let me increase its figure. Figure size, let's say it would be 12,5. So it just had given me the understanding, like, okay, item weight having positive coefficient. That means for each 1 unit increase in item weight, my sales value coming down by negative 0.0 something, right? Item fat count. So which one is having the highest coefficient? You know, these guys are like this. Okay. Here, these guys are getting a higher, very high coefficient value. But this interpretation is completely wrong. Okay. Now, why is it wrong? Okay. I'll tell you. See, for item MRP, you can see the coefficient value is very, very small. Isn't it? Item MRP coefficient value is very, very small. That means it is showing that item MRP is very less effective. It's like, you know, for one unit increase in item MRP, your sales is increased by 0.08. Okay. Now, how am I saying it is wrong? So let's try to do this thing that is called, you have a data frame. From where you take this or DF2. Okay, this is your data frame. From this thing, you have captured your X and Y. Right? So now let's say DF2 dot correlation. Okay. So when I find out the correlation, item MRP, if I compare with the sales, you can see I'm getting a good value over here, 0.56 compared to others. Okay. I can make it what? Let's say import more intuitive SNS, import C bond as SNS. Okay. SNS dot pair plot. Okay. Here I'll use annotation is equals to true. Okay. And then I will also make over here color map is equals to red, yellow, and green. Oh, sorry, heat map, not pair plot. I'm sorry. It's a heat map. No. Okay. So when I will plot the heat map, I'll show you the interesting fact over here. Okay. So now it's not a very good heat map, right? Because so many information is there. So let me increase the figure size. PLT dot figure size is equals to, let it be 20 cross 20. And I'll also make sure that format, that means the value that I'm getting should only be up to 2 decimal place. Then PLT dot zoom. All right. So now it is little better. I can make it more better by increasing the figure size more. Let it be 25 and 25. Okay, more better. So now if you see, the green color is showing the good correlation, right? Red color is showing the poor, green color is showing positive correlation. Okay, green color is showing the positive correlation, and this red color is showing what? Negative correlation. Red color is showing what? The negative correlation. All right. All the red color is negative correlation. Now, if I check it over here, here I have a 0.72. 0.72 with whom? 0.72, it's a very good correlation. It is having a correlation with item identifier non-consumable. Item identifier non-consumable with item type household. All right, no problem. Now let's say the sales column I'll take, because sales we are predicting, right? So where is sales over here? Item weight, visibility, outlet size, MRP, sales, right? So with the sales, we have the highest correlation. If I check with the sales, I have the highest correlation is MRP. Okay, with the sales, the highest correlation is what? MRP. But this correlation is highest, but this coefficient we are getting is very low. Okay, the coefficient that we are getting after the training, okay, is very low. So coefficient is very low, but correlation is very high. How is it possible? That means something is wrong. Okay, it's not possible for a good correlation we can get such a low coefficient. All right, coefficient is what? Not, over here the say this thing MRP coefficient. Okay, this MRP coefficient is not giving you the actual picture. Okay, so can anyone tell me the reason behind it? Can anyone tell me the reason behind it? Why is it so? Yeah, think. I'll tell you the reason. See, here we are using DF2. Okay, now I'm going to tell you one very interesting thing over here. I'm using linear regression. Linear regression uses this formula. Okay, like this. So linear regression try to find out these coefficient values. Okay, by tuning the error. Right. Now over here, the coefficient value will be tuned to minimize the error. Now let's say here I am giving a information as 0.3, and here I am giving a information as, let's say like this, 312, and here I am giving the information as 7. Right. So what happened? Your algorithm to minimize this error value will do what? Will try to tune these weights. In the process of tuning these weights, the feature whose magnitude is lesser, it will increase this weight. Because this information is very small, so it will increase this weight. And here this information is large, so it will decrease this weight. Right? Because if I will use over here same weight, if I use, let's say I'm using weight over here 1, or let's say 2. 2 multiplied by, let it be 1, 0.3 plus 2 multiplied by 312. Okay, so 2 multiplied by 0.3 will be 0.6, and 2 multiplied by 312 will be what? 624. So this, same magnitude can't be used. Okay, same label of, same level of coefficient, it can't be used. Right, here it will do what? If it is 2, it can be used over here, let's say 0.2. So if it is 0.2, then it will be what? 62.4. Okay, 62.4. Right. So the process will do what? The algorithm, when tune the process, it will consider the magnitude. Based on the magnitude, it is actually tuning these coefficient. Okay, it is not tuning the coefficient based upon the importance. Okay, it is not tuning the coefficient based on the importance of a column. It is not tuning the coefficient based on the importance of a feature. So here the coefficient we are getting is not actually representing the importance of the feature. So if I want that coefficient should be aligned with the importance of, if I want the coefficient should be aligned with the importance of the feature, then what should we do? Please tell me.
Min max scalar.
Nice. Now you are getting the things very nicely. Thanks. Okay, I was expecting this reason. Thank you. So that's why what we do here, that's why scaling is important. Okay. From SK11 dot pre-processing import main scalar. Okay. Scalar is equal to then features will get scaled only we do the scaling on features. And here we will do what? Scale input and log transformed value. So the the scaling here will not enhance your model performance. Okay, model performance will remain same. Okay, performance will not change. What will change? The model interpretation. Okay, it will just change the model interpretation. See the coefficient. Now, are we getting the coefficient for MRP higher? 1.97. Now it is correctly representing your, this model is now telling you the actual story. Now the coefficient of the model is now depends upon what? Depends upon the it is not depending upon the magnitude of the feature. It is now depending upon the importance of that particular column. Am I clear? Okay. Now that is it. I guess this much you should do for today. Okay. Tomorrow we will explore, we will do little bit more feature engineering. Okay. Like for example, tomorrow we will work on concept of multicollinearity. Multicollinearity. Like over here, you say these columns are having, like this column with respect to, like, let's see over here. This one. Okay. This one, outlet identifier 27. Okay. If I check it over here, just a minute. Okay. If I check this thing, outlet identifier 27 and outlet type, this one is 100%. They're having 100% that is correlation. Okay. Here outlet identifier 18 with this one. That means all the outlet identifier 18, all outlet identifier 18 is what is in supermarket 2. All outlet identifier 27 is in supermarket 3. Then why to use both the columns? We can use any one of them. Right? We can use any one of them. Right? So that's why if you check it out, supermarket 2 and 3 and outlet identifier 27. Outlet identifier 27. Okay, outlet 27. So this is outlet and 27 and supermarket 2 and 3. You can see over here, they're having the similar kind of coefficient. Okay. Right. So this is called multicollinearity. Same way, we have supermarket, other is what? This is supermarket 18 and outlet type supermarket 2. 18 and 2. 18 and 2. 18 and 2. Here we have 18. This is 18, right? And 2 is a use any one of them, right? Because both are giving the same information, right? And apart from that, what individually they are doing, like what is the individual effects they are having? Okay, that I can't decide. That is called multicollinearity because two columns are such highly collinear, right? There are two columns which are such having a highly collinear, this one and this one, right? And this one and this one. Okay, that how they are individually affecting the sales, we can't decide, right? So that is a problem of multicollinearity. And some other correlations are also there. Like here we have a very high correlation 0.72, right? So it's like we will also check, we'll also try to perform feature engineering and try to identify which columns should be used, which should not be used. Am I audible? Team, can you hear me?
Yes, sir.
Okay, so that's what we have to use. And for understanding that part, I have to explain one more thing to you, which is called adjusted R square. R square we had seen. We'll see adjusted R square, and with the help of adjusted R square, we'll work on the VIF. Okay, so tomorrow some very important concepts are going to be covered. Okay, which are important for your this whole machine learning tuning. Okay, that is called adjusted R squared. Okay, thereafter VIF, that is variance inflation factor. And if time permits, I'll also try to tell you tomorrow about the Flask API. That means if I have a model present, how can we create an API for deploying it? Okay. So that Flask API thing also I'll try to cover for you in tomorrow. All right. This particular thing we also work on for the deployment part. All right. Shall I close it for now? Any question to ask?
Yes, sir.
All good?
Yes, sir.
Yes, sir.
Varun, how are you?
Yeah, good, sir.
Varun, Varun, can you hear me? I don't know where is he. Sam, Varun. Okay, so I hope it's fine. Okay, we'll just go ahead from here in the next session. All right, Karthik. Yeah. All right, Savan, Karthik, Srividya, thank you.
Thank you, sir.
Okay. Thank you, sir.